Hello viewers, welcome to CEC lectures. Myself Dr. Preeti Jagwani from Department of Computer Science, Arabic College, University of Delhi. So in this series of operating system concepts, we are presently going through CPU scheduling algorithms, and we have seen we can say many CPU scheduling algorithms, and within this lecture we are going to explore our last submodule within this, which is multi-level feedback queue scheduling algorithm, and also we are going to explore the concept of deadlocks here. So let us start with our last scheduling algorithm, which is multi-level feedback queue scheduling. So multi-level feedback queue scheduling, in short, this is known as MLFQ CPU scheduling algorithm. It is actually like multi-level queue scheduling, which we have already seen in our previous lecture. But that multi-level queue scheduling was kind of, we have also seen in the disadvantage of that particular scheduling algorithm, that is inflexible algorithm. Inflexible as in, let's say for example, within that particular CPU scheduling algorithm, what we were doing, that the processes in the ready queue are actually assigned to some different queues according to their priority. So if there is a queue which is in the lower priority, there is a process which is in the lower priority queue, will not be allowed to move to the higher priority queue in any situation. So basically we can say that processes are not allowed to move between the queues. But here in multi-level feedback queue scheduling, if we talk about the term feedback, so feedback is something an information according to which we can modify the system. So if there is a feedback that the low priority processes are going into convoy effect or going into starvation, then these processes should be moved on to the high priority queues. So that means movement between the queues for various processes is allowed, based on some parameters or based on some feedback, that we will see what kind of feedback I am talking about here. So basically, because of this flexibility or because of this permission of movement, we can say this multi-level queue scheduling, multi-level feedback queue scheduling is much more efficient than multi-level queue scheduling. So if we can say characteristics of this multi-level queue scheduling algorithms are, in multi-level queue scheduling we have seen that processes are permanently assigned to a queue on entry to the system and not allowed to move between the queues. But if we talk about this multi-level feedback queue scheduling, this is not the scenario, because this multi-level queue scheduling is having a disadvantage of being inflexible, but the we can say advantage here is the low scheduling overhead, because the processes are permanently assigned to the queue. So multi-level queue scheduling is also having its plus and minus, having its pros and cons. So that setup was having an advantage of low scheduling overhead, because no movement of processes between the queues was allowed. But here in multi-level feedback queue scheduling, the idea is to separate the processes according to the characteristics of their CPU burst, and if the process uses too much CPU time, it will be moved to a lower priority queue. So that means this scheme is going to we can say a separation between input output bound and interactive processes in the higher priority queues. And in addition, a process that waits too long in a lower priority queue will also be moved to the higher priority queue based on some factors. And we can say this is kind of the aging policy. That's, let's say for example, after 10 minutes, if any lower priority process is not having its chance to get the control of CPU, some of them will be moved to higher priority queues. So some aging criteria is there to prevent the starvation. So Let us try to understand this multi-level feedback queue scheduling in detail. So we have, let's say we have 3 queues. So once a job is entered into the, kind of is taken from the ready queue, it is, a time quantum of 8 milliseconds has been decided by operating system, and it's a policy decision. So that particular queue is given the quantum for 8 seconds. If that particular process is, kind of not having or not, completed its processing, then it will be moved to the lower priority queue, which is given in the, kind of middle of the figure, which is having quantum is equals to 16. And if 8 milliseconds quantum is good enough for completion of its processing, or that is the burst time which a process is looking for, it may, kind of taken out from the CPU. So one arrow from the quantum is equals to 8q is going outside the system, and another arrow is going to take the process into the next queue, which is having quantum is equals to 16. So basically what is happening here, the queue is the process is entering, taking the CPU control for 8 milliseconds. If it is done with its processing, it will be taken out of the queue. If it is not done with the processing, it will be moved to the queue where quantum is equals to 16. Now with quantum is equals to 16, similar scenario has happened, that now if the job is complete, job has completed its CPU burst time and is done with the processing of CPU at least, so it will be taken out of the queue, or again it will be moved to a priority queue, which is or it is moved to a queue which is scheduled according to the policy of first come first serve. So here we are noticing one thing very aggressively, which is the kind of, we can say, movement of processes from one queue to another. And if we want to kind of see the advantages of this multi-level feedback queue scheduling, there are many. First thing, it is kind of more flexible. A job from the lower priority queue can move queue of higher priorities, and vice versa. If a higher priority job is kind of blocking the CPU for much time, then it will be moved to the lower priority queue thing. So that means the policy is flexible enough that it is allowing different processes to move between the different queues. But with this movements, there comes a price of CPU kind of, or we can say, scheduling overhead. Every time if you are allowing the movement between the queues, then there is going to be overhead of scheduling, and it is the most complex algorithm in order to we can say maintain. Because of this flexibility, processes are moving from one particular queue to another particular queue, and then so on and so forth. So then it involves kind of, we can say, a certain level of complexity also. So with this, we have seen this multi-level feedback queue scheduling. We have also compared this multi-level feedback queue scheduling with multi-level queue scheduling, which we have seen in the earlier lecture. And here we also with this multi-level feedback queue scheduling, we have kind of explored the scheduling algorithms, or the kind of, we can say, the prominent scheduling algorithms which are commonly used. So with this, let me allow me to move to the new topic of deadlocks. And this is kind of, we can say, it's not the entirely new topic. Yes, we have seen we talked about this deadlock thing in our previous lectures, but not in till greater length of detail. When we are going to do the series of operating system concepts, the concept of deadlock, its handling, then kind of its maintenance and its prevention is going to have its own importance. So let us begin with the topic of deadlock. So in a multi-programming environment, so first of all, let us try to kind of see what is a deadlock. In a multi-programming environment, we have various processes which are competing for resources, and let me recall that these resources are finite in number. We don't have infinite resources within a system. And when, let's say, a process requests for some resources, and the resources are not available at that particular time when the request was made. What process is going to do? That process enters a waiting state, we can say. So from kind of we can say a ready state, it may move to a waiting state. Now sometimes what is happening, that because of some situation, a waiting process is never again able to change its state to either kind of a ready, we can say. Why? Because the resources which it was looking for or which it has requested are held by other processes or other waiting processes more specifically. So the resources which a waiting process has requested are held by other waiting processes. So no particular process is kind of releasing its resource, waiting for other resources to get released, and this situation is called a deadlock. So for example, this is the most simple situation. If we can understand that we have a single railway track and there are kind of two trains coming from the opposite side, and now both of the train wants the other train to kind of get out of this track so that that one can pass. So that's a situation of deadlock. And if we talk about this situation of deadlocks, one important point which we need to be very careful about is instances of the resources. So for example, if a system has two CPUs, then the resource type CPU will have two instances. Similarly, a system can have multiple instances of the resource, let's say printer. So resource type printer may have 5 instances or may have 3 instances. CPU may have 4 instances if there are 2 CPU available. Now this point or this particular thing, we need to be very careful when we talk about the deadlock handling or kind of deadlock prevention, that a particular resource may have many instances. So what instances of which particular resource or how many instances of a particular resource are available, that is a point under consideration. So if a process requests an instance of a resource type, the allocation of any instance of that particular type should satisfy the request. So for example, we have kind of 4 similar printers in the system and a particular job is looking for a printer. So whether we are going to assign printer 1 or printer 2 or printer 3 or printer 4, that doesn't matter. The printer request of that particular job should be satisfied with the allocation of any instance of the printer. Now coming to please recall that we have we had many lectures about various synchronization tools, such as if you remember, mutex were there, mutex locks and semaphore. These are synchronization tools, but these synchronization tools are kind of, we can say, must be used very carefully, because these tools are on one hand these tools are considered as system resources, but on the other hand these tools or these synchronization tools more specifically are a common source of the deadlock. Now with this background, let us try to see what is the formal definition of a deadlock. So if you can see on the screen, a deadlock is a situation where a set of processes are blocked because each process is holding a particular resource and waiting for another resource which is already acquired by some other process. So I am just repeating the kind of definition: a situation where a set of processes are blocked because each process is holding a resource and each one of that each process is looking or waiting for another resource which is already acquired by some other process. So both all the processes are waiting for some resources to be released, and they have also blocked some resources, and no one is going to we can say progress, no one is going to proceed further. So let us try to understand this situation with the help of a figure which is given on the screen. So here we have two processes. So processes here are shown in the oval shape, while the resources, if you can see, shown in the rectangular shape. So we have two resources and two processes, process 1 and process 2, similarly resource 1 and resource 2. So we are let us start from the top and move anti-clockwise. So resource 1 is assigned to process 1. Resource 1 is with the process 1. Now process 1 is not ready to or not able to proceed further because it is waiting for the resource 2, and that resource 2 is already assigned to process 2. Now why this process 2 is not we can say releasing the resource 2, because it is waiting for resource 1 in order to proceed further. So if we can see here, process 1 and is having resource 1 looking for resource 2, process 2 is having resource 2 looking for resource 1 or waiting for resource 1. So in this situation, neither of these processes, nor the process 1, neither the process 1 nor the process 2 is ready to release the resource which they are having. They are just sitting idle, we can say, or not able to proceed because their requirement in terms of resources is blocked. Whatever resources they are having are not to make them proceed further. They are looking for more resources. More resources they cannot get because these more resources are already blocked by other process. So in this situation, neither of them is able to proceed, and this is a situation which we call as deadlock. Now if we try to see why these deadlocks occur, we need to understand the whole flow of a normal mode of operation when a process is looking for some resources or a process needs to utilize some resources. So in order, the normal flow of operation when a process wants to utilize a resource should be of the should have the following sequence. First is the request thing, next is the use, and third one is the release. So request says that the process requests the resource, and if the resource cannot be granted immediately, for let us say it is being used by another process, then the requesting process must wait until it can acquire the resource. So it will the process is going to submit its request. If it is going to get the resource, perfectly fine. If it is not going to get the resource, then it should wait until it can acquire the resource. So that's the phase of request. Then a process who has already got the requested resource, the process can operate on the resource. For example, if it is a printer, the process can print on the printer, and after use there will be third phase, which is of release. In this particular phase, the process releases the resources. So first of all, it will request for the resource. If got, fine enough. If not, then it will wait for the resource. After getting the resource, it will use the resource, and then it is going to release the resource. Now when we talk about this deadlock situation, somewhere there is we can say hindrance in this normal flow of operation in which we talk about request, use and release. So either the processes are not releasing the resource or something of that sort. That means this normal flow of 3 steps is going to be interrupted. I'll come back to this topic, I'll come back to this situation once again, but before proceeding, let us try to understand why this deadlock situation is going to arise. So a system will be having 4 conditions simultaneously in order to for a deadlock to arrive, or we can say a deadlock situation can arise if the following 4 conditions hold simultaneously in a system. Now what are these 4 conditions? These 4 conditions are of mutual exclusion, hold and wait, no preemption and the circular wait. Now let us try to understand these conditions one by one. So the first condition was mutual exclusion. So mutual exclusion says at least one resource must be held in a non-shareable mode, that is only one process at a time is going to use or is allowed to use a particular resource. If the another process is requesting that resource, that another process or the requesting process must be kind of delayed or must wait until the resource has been released by the previous one. So that is the condition of mutual exclusion, in which we say that one resource can be held by one particular process exclusively. Now coming to the next condition, which is of hold and wait. So hold and wait condition says that a process must be holding at least one resource and waiting to acquire additional resources that are currently being held by other processes. So this is the condition of hold and wait, in which we say that one process is holding one resource and also waiting for another resource, and that resource is not available. Why? Because that resource is already we can say held by other process. So this is the condition of hold and wait. The third condition is about no preemption. So preemption, as we seen, is kind of we can say forcefully taking the control of a particular resource. So if we talk about the condition no preemption, that means resources cannot be preempted. That is, a resource cannot be released only voluntarily by the process holding it after that the process has completed a start. That means the process is, we can say, is not ready to preempt the resources or not ready to release the resource voluntarily. That is the condition of no preemption. And the last one is the condition of the circular wait. Now in order to understand the circular wait, let us assume a scenario in which there is a set of n processes, let us say start n plus 1 processes starting from P0 to P1, P3, P2, P3 till Pn. These are the waiting processes. And now what is the kind of we can say scenario between these processes? P0 is waiting for a resource which is held by P1, P1 is waiting for a resource which is held by P2, and then so on and so forth. Pn minus 1 is waiting for a resource which is held by Pn, and Pn is waiting for a resource to be held by P0. So all these processes starting from P0 to Pn are, we can say, waiting in a kind of circular mode. P0 is waiting for P1 resources which are with P1, then P1 is waiting for the resources which are with P2, P2 is waiting for the resources with P3, and at last P1 is also waiting for a resource which is held by P0. So all these processes are waiting for one another in a kind of, we can say, circular fashion. So we have seen these 4 conditions. One is mutual exclusion. At least one resource is there which is going to be kind of used in a non-shareable mode. That means one process, if going to get the control of that particular resource, will be kind of holding it exclusively. Then another one is the condition of hold and wait, in which a process must be holding at least one resource and waiting to require additional resources that are currently being held by other processes. So holding some resources, waiting for other resources, and then so on and so forth. Then no preemption, that means resources cannot be preempted by the system. That means resources are only voluntarily released by the processes when they are done with those resources. That means after that the process has completed its task, these resources cannot be preempted. Once a process has acquired a resource, system cannot preempt these resources. And the fourth one was the condition of circular wait, which was the scenario of all the jobs waiting for one another in a circular fashion, and they are waiting for the resource which is occupied by the which is held by the another process. So all these conditions which are mutual exclusion, hold and wait, no preemption and circular wait, all these four conditions must hold simultaneously for a deadlock to occur. But here one thing which is very important here is the conditions, all these four conditions are not completely independent. They are if we when we will be able to see them in detail in our upcoming lectures, I will explain these are kind of interdependent conditions. These are not completely independent in the as in the circular wait condition implies hold and wait. So circular wait is one job is waiting for another, and the second job is waiting for the third one, and so on and so forth. So this is actually a condition which implies hold and wait. So all these four conditions are not completely independent, but the significance of these four conditions is that all these four conditions must hold for a deadlock to occur in a particular system. And if we want the deadlock, if we want to avoid that deadlock, we should kind of hit on these four conditions. So in this lecture we have started with multi-level feedback queue scheduling, and after understanding the multi-level feedback queue scheduling algorithm, we started with deadlock. We have seen the concept with the help of an example, and we have also seen what are the necessary conditions which are kind of we can say which are required in order for a system to occur in a or stuck in a deadlock. And here is a list of references which is being used for the preparation of the lecture. Hope you had enjoyed it. See you in the next lecture. Goodbye.